An important feature of quadratic functions is that their vertex represents a unique maximum or minimum point, depending on whether the parabola opens downward or upward. In applications, these extreme values are typically important, so we want a way to be able to find these. Let's begin with a typical quadratic in general form. If we're interested in finding the vertex of this quadratic, then putting it into standard form would be desirable, and we accomplished this before by completing the square. The slight difference this time is that the coefficient a may not be 1, and our advice about using half of b squared is not applicable. I factored out a from the x squared and the x terms, but I have no need to do it for c, so we've left c alone. If I just think of the terms inside the parentheses and disregard everything else, I'm back in the situation where the coefficient of x squared is 1. So I should add half of the coefficient of x squared to complete the square. So that's b divided by 2a, all squared, which becomes b squared divided by 4a squared. So I add and subtract this inside the parentheses. I'm still working just inside the parentheses and disregarding everything else. So inside the parentheses, I've added and subtracted this term. If I look at the x squared plus bx plus the green b squared over 4a squared, then this will factor to x plus b over 2a squared. We haven't utilized the term in blue. It was just there to balance out the equation. Now that we have this perfect square, I can distribute the a, and I have this quadratic written in a messy standard form. It may not look exactly like standard form at first glance, but remember that for any quadratic you could choose, a, b, and c are just some fixed numbers. So b divided by 2a is just a number, as is c minus b squared over 4a. So those are my values of h and k in the standard form. So to summarize all of that work, the quadratic function ax squared plus bx plus c has its vertex at coordinates negative b over 2a, because that's our value of h in the standard form we just produced. And the y-coordinate is c minus b squared over 4a, because that's the value of k in the standard form we just produced. To cut down on the memorization slightly, we could just say that the x-coordinate is at negative b over 2a. Then the y-coordinate that corresponds to that x-coordinate is obtained by just plugging that x-coordinate back into the function. So from the algebraic viewpoint, we would be interested in saying that the function attains its maximum or minimum value, depending on whether the parabola opens downward or upward. From a graphical viewpoint, we might simply say that the vertex of that parabola is at these same coordinates. In the picture on the left, the vertex corresponds to a minimum y value, and in the picture on the right, the vertex corresponds to a maximum y value. Let's look at an example of all this. Suppose the gas mileage in miles per gallon that you achieve in your car while traveling at speed s is given by this function. So this function asks for your current speed and determines the gas mileage you're receiving at that speed. If we look at the graph, it indicates that traveling at a low speed, which is our s-axis, gives us a low gas mileage. But traveling at too high of a speed also reduces the gas mileage. Somewhere a little over 40 miles per hour, we achieve a maximum gas mileage of just a little over 30 miles per gallon. So could we get a better estimate for these two questions? At what speed is the best gas mileage obtained? And what is that gas mileage? Determining the coordinates of that vertex answers both of these questions. The x-coordinate of the vertex is negative b over 2a. We have to refer to our general form to see that b is 3 and a is negative 1 over 28. All of that reduces down to 42. So the speed that we should be driving to get the best gas mileage is 42 miles per hour. Since I know the x-coordinate of the vertex is 42, then to determine the y-coordinate, I can simply plug it into the function. The gas mileage I obtain by traveling at 42 miles per hour is given by substituting 42 for s in that equation, and it becomes 32 miles per gallon.